Hello friends and welcome back to VHB tutorials. So in today's video we will derive a most important relationship, that is stress, strain and displacement relationship of the nodes. So in this video you can find how to find the stresses for the different elements, how to find the strain in these different elements, and how to find the displacement or the strain in between the elements without considering that point as a node. So please stay tuned to this video and watch this video till the end, and in between if you have any doubts then you can ask me in the comment section, and you can reach me on my Instagram handle. I will provide the link in the description. So in that handle also you can message me and ask the doubts, so you can clear the doubts, right? So please watch the video till the end. If you have any doubts then you can ask me, and don't forget to subscribe my channel, and please share this video as much as you can share, right? So now let's dive into our today's video. So now we'll start. So for that, first we will consider a 1D bar element. So for example, we have element E having node 1 and node 2, right? Now we will derive the relationship between displacement, stress and strain. So as the name, stress, strain, so the first thing come in your mind or should pop up in your mind a Hooke's law. So there will be some use of Hooke's law in this derivation. Why? Because the name, stress and strain are included in this topic, right? So the first thing you should pop up, or there should be a intuition in your mind that yes, at some point here we will use Hooke's law. So now till now I assume that all of you know the Hooke's law. There is no need to explain the importance of Hooke's law or the formula of Hooke's law, right? So first we will consider a 1D bar element. So first line you have to write that considering 1D bar element. So according to Hooke's law, stress is directly proportional to what? Strain, right? This is the Hooke's law. Stress is directly proportional to strain. So stress is normally represented by sigma, which is proportional to strain. Strain is what? Epsilon. Now removing this proportionality sign, we are getting E into epsilon. Now what is this E? E is nothing but Young's modulus or modulus of elasticity. What is the unit of E? Yes, it is Newton per meter square or mm square. Here we are dealing with the element, so we will consider mm, Newton per mm square. What is the unit for strain? Strain is a unitless quantity. Why? Because strain is defined as deflection upon original length or change in length upon original length. So length upon length, it is in the ratio. So it will be cancelled. So strain will be unitless. And what is the unit of stress? It is also Newton per mm square. Why? Because stress is defined as force per unit area. So Newton per mm square. Now here we are getting a what? We are getting Hooke's law. So what will be the next step? So the next step is we will consider this element as a very small element, and there will be a strain in this element. So that strain, why there is a strain? Because we are applying force here. So as we are applying force at node 2, so there will be a strain, there will be a deflection, right? So that deflection, this is a small element. So the deflection of this small element is represented by what? Epsilon. So strain in that small element, or let me write here. So strain in this small element is given by epsilon is equals to what? Change in length du upon dx. Now why du upon dx? Means we are considering change in length as u, right? This is deflection. Let's say, right, we will write deflection. Now what is x? So if you know that in previous videos we have discussed different coordinate system. So let's say this is a distance x, this is a reference axis, this is reference axis. So from this axis the distance of node 2 is x, the distance of node 1 is x1, and the distance of node 2 is x2. So the length will be what? x2 minus x1 of this element, right? So we are considering a small element. So the length of this small element is considered as x. So this is the length. This is the big element, but we are considering the small part of this element. So we will consider that length as x. And what will be the deflection in that small part? In that small part, the deflection will be d u, and what is the small length of that element? It is dx, right? So this is change deflection upon original length. I will explain again. This is our normal representation of 1D bar element. Means this is our reference axis. From this reference axis, the node 1, the distance of node 1 is x1 and the distance of node 2 is x2. So what will be the length? It will be x2 minus x1. Right? This is our whole 1D bar element. Now we are considering a small part of this element. So for that small part, what will be the deflection? So for that small part, the deflection would be du, right? Change in length. And what is the length of that small part? The original length of that small part is small length dx. So the strain in that small element is represented by what? Small deflection upon the length. So it is deflection upon length. So it is du by dx, right? So I hope you got this. Now, remember this key rule. Whatever you get in FEA, means whatever coordinate system you get in FEA, convert that coordinate system into natural coordinate system. Why? Because natural coordinate system is a unitless quantity. And you know the natural coordinate system lies between -1 to 1. So converting any other coordinate system into natural coordinate system will be very easy, and when you will solve the natural coordinate system, you will find that it is very easy to solve that natural coordinate system. So always try to convert a different coordinate system which is given to you into natural coordinate system. So this same phenomena we will use here. So as we have this different Cartesian coordinates, let's say we are for now we are considering this x as a local coordinate system, right? Just we are taking this for understanding. So here we have local coordinate system. Our strain is in a local coordinate system. So now we will convert it into a natural coordinate system. So how we can convert? If you know the chain rule of differentiation, then it will be very easy to convert this into natural coordinate system. So how we can convert it, we will see here. So now after this line, after this equation, we will write as per the chain rule of differentiation, this equation can be given as du by d zeta into d zeta by dx. Now what is this zeta? Zeta is the natural coordinate. The significance of natural coordinate, shape function and different types of coordinate system I will explain in the separate video, right? But for now, just remember this d zeta is the natural coordinates, right? So this is how we can convert our local coordinates component into natural coordinate by using chain rule of differentiation. Now our 50% of work is finished. Why? Because now we just have to find the values of this, and after that we will keep the we will put the values in this equation. Let's say equation number 1, this is equation number 2, and this is equation number 3. So now what we will do, we will find these values, values of this and values of this, right? So for that I have to rub some of the parts. So let's say I will rub this part. So what is this u? So u is given by u is equals to n1 q1 plus n2 q2. Now where this u is used? So suppose that I will explain in a brief that what this the significance of this formula, but in detail I will make a separate video on this shape function, this u and the properties of shape function, right? In that I will explain you in detail, but now for now I will explain in brief. So what this u, where this formula is used? Suppose that you have a element E having node 1 and 2. Now to find the displacement of the nodes, to find the displacement at these nodes, node 1 and node 2, is very easy, and we have the formula that F is equals to KQ, and using this formula we can find the displacement at the nodes. That video is already uploaded in my playlist, means problems on 1D bar element. In that you can find that we can easily find the displacement of these nodes. But what if you want to find the displacement in between this element? Means suppose that you are thinking that, let's say, means I want to find the displacement at this point P. Then what you will do? Then you don't have any formula to find that displacement at point P. So two methods we have. Number one, that at point P we have to define a node, right? So after defining this node, we are discussing this first method, means defining the point as a node at which we want to find the displacement. So we are defining this point P as a node, so we are having 3 nodes. And now we are using this formula, this global stiffness formula. Then what will be the order of global stiffness? So order of global stiffness will be what? It will be total number of nodes. Here we have 3 nodes into degree of freedom of each node. So we know degree of freedom of each node will be 1. So it is 3. So the order of global stiffness matrix will be 3 cross 3. That means the order is increasing. Now suppose if you want to find the displacement at this point, let's say P dash, then how many nodes are there? Here we have 1, 2, 3 and 4 nodes. So the order increases, and now order increases, and as we have to solve this global stiffness matrix on the pen and paper, so it will be very difficult for us to solve by considering the nodes at the different points at which we want to find the displacement. So this first method can't be used on the pen and paper format. So what we will do to make easy the calculation, so don't worry, we have a beautiful formula by which we can find the displacement at any points in the elements. So just observe. So the same problem, now I want to find the displacement at this point, let's say P dash. Now we are not considering this point P dash as a node. Now what we will do, we have a formula called this. This is a formula by which we can find the displacement at any points, provided you should have the values of n1, n2 and q1 and q2 can be calculated from this formula, that is F is equals to kq. So you will be having q and you will be having n1 and n2, then you can easily find this u, right? So this is the formula by which you can find the displacement at any point inside this element without considering that point as a node. So this is a brief introduction. Don't worry, I will explain this formula in detail. And also this formula, the derivation of this formula is not in our syllabus. If you want to see the derivation, then it will be given in any standard books, so you can go through that derivation. But in our syllabus there is no need to derive. So we will just see the overview, means we will just discuss the significance of this formula and how to use this formula. We will discuss in the next video, in which I will explain you in detail. So this formula is used to find the displacement inside the element without considering that point as a node, right? So this formula is used for 1D bar element only, right? So remember that this formula is true for 1D bar element. Now if you have other type of element, then for that element we will have different formula for this u, right? U is any displacement. Suppose that this point is I am applying force here and this point moves in this direction, and now we want to find the displacement. Then this displacement is represented as u, and you can find as n1 q1 plus n2 q2. Now what is n1 and n2? n1 is the shape function of node 1 and n2 is the shape function of node 2. Now what is shape function? Means we are suppose that you have a 5-year-old child in front of you. Now we want to analyze his behavior, means how he behave, how he do some different things, right? So what you are doing, you are analyzing the behavior of that 5-year-old child. So the same way we want to analyze the behavior of this node, means how this node will displace in right direction or in left direction. That means in positive x or negative y, in negative x, right? So the behavior, the analysis of the behavior of this node 1 is given by shape function n1, right? So n1 is given by 1 minus zeta upon 2 and n2 is given by 1 plus zeta upon 2. Don't worry, this derivation we will do in the next class. This derivation is in our syllabus. So this n1 and n2 refers to the behavior of this node, means how these nodes displace in particular direction. So that information is given by this shape function, and interpolating this shape functions we can find the displacement in between this element at any point without considering that point as a node. So I hope you got the idea, means a rough intuition that what is shape function, what is u and how it is used, right? So we have this formula u. So what we will do, we will differentiate with respect to zeta. But before differentiating with respect to zeta, we have to convert this shape function into zeta terms. So just observe me. So this is u, n1 is given by 1 minus zeta upon 2 into q1. q1 is the nodal displacement, and n2 is given by 1 plus zeta upon 2 into Q2. Don't worry, the derivation of N1 and N2 I will derive in the next video. So that derivation is in our syllabus. So don't worry, for now just remember this N1 is given by 1 minus, this is zeta upon 2, and N2 is given by 1 plus zeta upon 2, right? Now we can differentiate. So differentiating this above equation with respect to zeta, we can have this 1 by 2 is constant, so 0 minus zeta upon 2, so it will be minus 1 by 2 q1, and plus again 1 by 2 is constant, so 0 plus this zeta upon 2 is 1 by 2 into q2, right? So we can write minus q1 plus q2 upon 2. Keep this minus q1 at first, and after that you can write q2. Why? Because you will have a formula, so in this way you can easily remember that formula. So keep this in this way only. Now after getting du by d zeta, we want to find this zeta. So now we have the relationship between zeta and the natural coordinate. So that formula, so this derivation is also not important, because as this the formula is important but derivation is not important, as this derivation is not in our syllabus. So the zeta or the natural coordinate in terms of local coordinates or Cartesian coordinate is given by x minus x1 upon x2 minus x1 into 2 minus 1, right? So this is the formula which relates natural coordinate, this is a natural coordinate, and this x is the Cartesian coordinate, right? So this is the relationship between natural coordinate and Cartesian coordinate. Now what we will do, we will differentiate this. So we have d zeta upon dx, so this is x upon x2 minus x1. Now what is x2 minus x1? x2 minus x1 is the length of our element L. So this is what, x upon x2 minus x1 minus x1 upon x2 minus x1, right? So this x is variable, so what we will have in differentiation, it will be 1 upon x2 minus x1, and this term is constant, x1 x2 x1. So this is why this is constant, because this distance is a particular distance and it is fixed, and this x2 is also constant, this is a fixed distance, so it will be constant term. So this will be 0 into 2, and this 1 is also constant, so 0. So what you are getting, it is 2 upon x2 minus x1. So it is d zeta upon dx. Now what we will do, we will substitute these both the values in above equation. So what is du upon d zeta? It is minus q1 plus q2 upon 2 into, what is d zeta upon dx? It is 2 divided by x2 minus x1, right? So this gets cancelled. So we are getting minus q1 plus q2 upon x2 minus x1, right? This q1, q2 are what? Are the nodal displacement. x2 minus x1 is what? Is the length of this element. So it is epsilon. Now in FEA we all know that we have to convert this formula into matrix form. So how we can convert? This length is a constant term, so we are bringing out, so it is 1 upon L. I am representing x2 minus x1 as now L. So we have what? We have this term minus q1 plus q2. So how we can represent this term into matrix form? It is a 1 cross 1 matrix. So we want to bring 1 cross 1 matrix here. So how we can bring 1 cross 1 matrix? Multiplying the row matrix with column matrix. So that means, observe here, I am keeping minus 1 1 and here q1 q2, right? So this is what? This is the row matrix of order 1 cross 2, and this is 2 cross 1. So we are getting 1 cross 1 after multiplication. So this is how we can get 1 cross 1 matrix, by multiplying row matrix with column matrix. So in this place, what we will write? We can write matrix as first as row minus 1 1, and here you can write q1 q2. So when you will multiply this both the matrix, then you will get this only, right? So this is minus 1 1 q2 q1. So now we can represent this term as b, right? So this term we are representing with b, and this term q1 and q2 we can represent it with what? With small with only q. So this epsilon is what? B into q. So you will get this formula in your textbook, that b into q. B represent this term and q represent this term. I will write perfectly. So this is b is what? B is 1 upon L into minus 1 1 and Q is what? Q is equals to Q1, Q2, right? Now the name of this matrix is important. So what is the name of this matrix? Now how to remember this name? This is what? This is strain. This is what? Element. So the name of this matrix will be elemental strain displacement matrix. I will write and then explain again. So now the name is important, means you have to remember what is this name of this B. So this is what we are deriving for an element. So first we will have element. Now what is this? B is in the formula of strain. So element strain, and here with strain we have the displacement of Q. So element strain displacement, and as this is matrix, so we can write as matrix. So what is B altogether? B is what? Element strain displacement matrix. So means if you can means in the examination you could ask to find or to derive the elemental strain displacement matrix. At that time you have to derive up to this much part only, right? And if you are asked to find this this whole displacement stress and strain relationship, then just you have to keep these values of epsilon into equation of Hooke's law, that is sigma equals to E into epsilon. So here we will put the formula. So what is epsilon? Sigma is equals to capital E into B into Q. So we know what is the values of B and what is the values of Q. Just by putting the values you can find the stress, right? So this is the derivation for displacement, stress and strain relationship. So this is over. So today's video is completed. In next video I will discuss what is shape function, what is the significance of shape function, then properties of shape function, different types of coordinate system, and the significance of natural coordinate, right? So if you have any doubts, then you can ask me in the comment section, and please don't forget to subscribe my channel and share this video so your friends can be benefited, right? So stay safe and bye till the next video.